Suppose we have a classification problem. We have a linear classifier, and then we say, and this data sets are linearly separable, and now we have two solutions. And the question, which solution is better? And clearly, on these two examples here, we kind of intuitively understand that the solution on the right side is better solutions. And and how to achieve the solution, and there's multiple ways to do that. One is by designing a better loss function. So the loss function will kind of encourage you to separate these two group of points. That's what we did previously. For instance, we talked about this kind of a cross entropy based loss function. And if you apply this loss function, then as a byproduct of that, you will tend to encourage the solution look like the right-hand side of the solution. And for the algorithm that does not use the loss function, and then they could potentially produce a solution on the left side. So for instance, the perceptual learning algorithm could well just generate a solution on the left side, and then the algorithm will stop. So that's very well a legitimate solution for the perceptual algorithm. So that's what we talked about last time. But however, we want to look at it more closely. So we will closely want to say, in what sense we want to say this true solution is better than the other one, instead of using a surrogate loss function. And we want to set up some kind of objective in the very beginning of that. And that's what we talked about last time. So we introduced this concept of a margin. So let's review what we talked about last time. So we said last time saying this, we're still in a context, we'll think about a linear classifier. And in the context SVM, we're going to use this notation here. So using this, using the w dot x here plus b, and use this my linear predictive scores of that. And we say if this guy is positive, we predict label to be 1. If this is negative, predict label to be 0. However, in general, if you just take a sign of this functions here, there is this kind of a invariance associated with these functions here. For instance, you can rescale this function by a constant number, and that doesn't change the prediction. So as a purpose of the kind of a learning purpose, I want to eliminate this type of the redundancy here. So the way of remove this redundancy, we're going to constrain such that we set up two boundaries, such that we want the solution on the right-hand side here to be strictly greater or equal than 1. So that's the 1 is a choice of a parameter that remove the redundancy of that. And on the regions of -1, we want this score to be less or equal than -1. So that will be 2 regions we specified that. So by doing that, now you remove the redundancy in the WX of that. So that's what we're going to stick with. We're going to say this. We're going to say for all the dots that is labeled with 1 on the right-hand side here, in this side here, we would like to have this w dot x plus b greater or equal than 1 for all the dots here. And for the blue dots on the bottom left corner here, we want all the score to be strictly less than -1. And these are the constraints we're going to impose on these functions here. And then the question is this, right? So there are still many solutions can produce you this type of, satisfy this type of constraints you have. And then what do we say this? We want to maximize the margins between these two here. And that is this step here we talked about last time, the distance between these two separating in the hyperplane. So in general, in 2 dimensions is a line here. You can see 2 lines, but in 3 dimensions, now these 2 lines become 2 planes. And then we can talk the distance between these 2 planes. And of course, in a higher dimension, we talk about something called a hyperplane. In general, these guys here would be a hyperplane. And because these 2 planes are parallel to each other, so we can talk the distance between these 2 planes here. And that is this guys that we talked about here. This is something called a margin. And this guys here is w dot x plus b exactly equal to 1. This guys here w dot x plus b minus 1. So once you constrain the system in this way, and then last time we talked about how do we calculate the margins. And then in the end, it turns out the margin is simply the 2 over the square normal w, this normal vectors of the lines, of the separating planes. And that is the margin. And So the margin is inversely related to the norms of the W, right? So that's what we said last time here. Oh, no, sorry, this is the R here. Margin is here. Margin is 2 over the norm of W. So the margin is equal to 2 over the norms of W. So that's the margin we talked about here. This is M here, right? And now, suppose say we're going to identify a classifier such that I want to maximize the margin. So maximize, push those two separating planes as far as possible. We want to maximize margin, while at the same time, we want to make sure that the dots labeled with 1 are above these planes here, and dots labeled with -1 are below this, the other hyperplane, the boundary hyperplane. And by doing that, we formulate the problem as optimization problem. But different from the previous one here, the optimization have a set of constraints we have. And that was written in this side here. So because we want to maximize the margins here, so that is equivalent to minimize the norms of W or square norms of W. So that was written in this guys here. We're going to minimize the norms of W. So this guys here equal to norms of W squared. So minimize the norm of W is equivalent to maximize the margin. So for in general, we written in this way. However, we want to have set of constraints to be satisfied. So in particular, if your sample is labeled with 1, and we want to make sure that that is indeed above this boundary plane. On the other hand, if your data is labeled with -1, we want to show it's below this, the other boundary hyperplane. So these are constraints we have. Overall, we have M constraints. M is the number of samples. Because for each sample, we have 1 constraint. Essentially, we want to say that we want this sample to be correctly classified above these separating planes. And that is the problem we're going to formulate here. So let me rewrite here, because that's the important one we talked about so far. So, so in the language we talked about here. So first of all, what's the data here? So data here is the xj, yj here. So that's the data we have. And now we have I goes from 1 to n. So that's the data we have. And in this case here, the x, in general, xj is n-dimensional. And yj now is a binary. It can be -1 or 1. So on 2 labels here. So the convention here is slightly different from the convention we use for binary classification. So in the case of binary classification, we use a 0, 1. So in this case, -1, 1 here. So that's the data. And then now the model is the same as before. The model is the linear models here. And then there will be you have 2 parameters here. One is W, and then W dot X here plus B, and the linear response here. And if this guy here is greater than and then 0, you say the predicted label is 1. If less than 0, predicted label is -1. So that's the model, predictive models here. However, for the learning here, we formulate as optimization problem. So in the optimization problem, we're saying this, we want to maximize the margin. So equivalent, we say, that is equivalent to say minimize the norms of W. Right, so the subject, however, you have several constraints. We have subject to a set of constraints we have here. So the constraints, we have M constraint. So the constraint we're saying is, so the W dot Xi sample plus B ought to be greater than equal than 1 if your Yi is equal to 1. It's target level 1 here. And then otherwise, if this Yi here is equal to -1, we want to make sure that this score is below that separating hyperplanes. So that's 2 constraints we have here. That's 2 constraints. So even though we have 2 constraints, in fact, only one of them is true. So overall, we have M constraints. So sometimes, and the people want to simplify the notations here. So one way of simplifying the notation is to combine these 2 constraints here and using 1 constraint. So one way you can do this is doing this. So you say, well, I can combine this on here. I can do yi dot w, say, this is the score here, plus b is greater or equal than 1. So and now we combine, you can merge with this one notations here. Well, let's think about and how this will be reduced to the previous one. Well, if yi is 1, so that's the same as the constraint we have. If yi is equal to minus 1, and this say minus 1 should be greater than, minus the score is greater or equal than 1, so which means that equivalent is saying that the score itself is less or equal than minus 1. You can see now these two are actually equivalent. So as a result, and then we simply, and then we rewrite the problem something like this. So much simplified notation is simply say, we're going to minimize the norms of W, and then subject to the constraints to be compacted, writing down to be yi times dot xi here plus b. So this is a score, the scatter score here. This is greater or equal than 1 for all I. For all I goes from 1 to m. So you have that m constraints you have. So his minimization is with respect to both w and b here. So you have two sets of parameters. Overall, you have n plus 1 parameters here. So that is the problem we're going to solve here. In fact, the w returned by this solution here was simply this problem here. And this is optimization problem. So the question is, what are the solutions to this problem? What are the kind of basic characters and how to characterize solution to this problem here? So, so this type of problem is something you call a constraint optimization problem, because unlike the problem we talked about so far, the constraint optimization problem. So it's different from the problem we talked about previous now. So everything we talked about, we say we formulate a loss function, we want to minimize it. So in this case here, so you minimize some function, but at the same time, you have a set of constraints that this solution need to satisfy. So, so the problem here is much harder to solve than the unconstrained optimization problem. So for instance, you cannot naively apply a gradient descent to this problem here, because your gradient directions, gradient of your loss function, or the objective function here, may violate those constraints. Once you update it, may violate the constraints. So that's not good, right? So because constraints is not satisfied. So we need to use a few other methodology to solve this problem. So then today I'm going to talk about some of this method for solving this problem here, right? So one of the main ideas of solving this problem is by introducing something called a Lagrangian multiplier, and for constraint optimization problem. So, so that's what we're going to talk about today here. So the way we're doing this is this. So again, now we're going to think about how to solve this problem here, and the question, how do we solve that? So right now I have two sets of, let's review again. We have this objective function. This is the square norms of the W here, but we have this constraint here, And now let's simply, so the constraint is the same as what I wrote down previously here. So suppose now you treat them as, say, and you have this WB here, you have the G parameter theta here. The theta here is the two represent both W and B. Suppose you collectively represent B as a theta parameter here. And then I'm going to write down my G theta here to be 1 minus this guy's here, okay? So now if you do that, if you do this way here, let's go back to what I written in this side here. Suppose you define, let's define Gi theta to be 1 minus yi w dot xi plus b. Suppose I define that. So right now, theta essentially, theta is equal to W and B here, essentially, just as a notation convenience. So I don't need to write down W and B, to get two of them. And then this problem, the optimization problem is essentially written down as this. You have this objective function W here, but then subject to the constraints to be G I theta less or equal than 0 for I goes from 1 to m. You still have m constraints here, but I'm going to simplify the notation. I'm going to need to only focus on discussions of Gi theta. Okay, so what I've done so far is that's just a change of the notations. Define the G sub I theta to be these guys here, but otherwise the problem stays the same. Didn't change anything. So next I'm going to do one thing here. So that's slightly a big step forward here. So what I'm going to do here is, so I'm going to try to remove this constraints here. And how do I remove this constraint? I'm going to introduce this constraints into this object function, the normal W here. So how do I do that? Well, so the way I do it, I'm going to construct something called Lagrangian function. Something called Lagrangian. So Lagrangian function is something like this. So I'm going to keep the original objective function W squared here, but then I'm going to do something like this. Summations of alpha sub I times G I theta here. I'm going to move this G sub I theta into this original objective function here. And then I'm going to do summation over where I goes from 1 to m. Okay? So I'm going to introduce a function look like this guy here. But now let's do this. Suppose I want to maximize this function with respect to theta first. So let's think about this function here. Suppose I want to solve this problem here without any constraints. So this is an unconstrained optimization problem with W fixed. W is treated as a constant value. So I'm only trying to maximize maximize not theta. Sorry, I made a mistake here. I can maximize over alpha, but the alpha is constrained to be a positive. Suppose I'm going to think about this problem here. What is the solutions of this problem here, if you think about it? Okay, so let's think about it here. What solutions to this problem here? There are several possibilities here. So first of all, so I introduce something called alpha sub I, one variable for each one of the constraints, G sub I theta here. And so suppose I want to solve this problem here, maximizing over alpha here, only maximize with respect to alpha, this new variable I introduced here. Everything else stays the same. I just treat them as a constant. So what are the solutions in this problem? Well, this problem is an optimization problem, but it's a very relatively simple optimization problem because it's only a kind of linear functions with respect to alpha. So that's easy to do. And then the maximizations here, and then you know the values. So the values depend on this. So what happens if Gi theta depends on this constant here? What happens if this G sub I theta is greater than 0? So what happens in this case? If it's greater than 0, it's positive, right? If this guy is here, somewhat is positive here. And now if you're maximizing those guys with respect to alpha, so what will be the solution? Well, solution obviously would be, positive infinity, because if I have a positive constant associated with linear function here, in order to maximize over alpha sub I, what I can do, I can choose alpha sub I to be infinitely large. So as a result, that you get a positive infinite numbers here. So that's very straight. So as long as any one of them here is positive, and then the solutions to this maximization problem is simply the positive infinity by choosing alpha sub I to be very, very large number. So that's clear. And what happens on the other hand, if G sub I theta is non-positive, less or equal than 0, what would be the maximal solutions of this problem here? Well, in this case here, because it's negative here, if I want this, make this number to be positive, to be maximal, which value should I choose? Well, I'm going to choose alpha sub I to be 0. Okay, the reason, because as long as alpha sub I is not 0, any positive number, I get negative numbers with that. So maximum value will be 0 in this case here. If I choose G sub I to be if constrained to be negative, and that will be 0 here. And the 0 is achieved when alpha sub I taking and next to be 0 values, right? So now let's suppose, so that's the optimized solutions optimization with respect to alpha here. But now let's combine these two here. Suppose now I want to do this. I want to go back this slide here. I want to say I want to now maximize over alpha. At the same time, I want to minimize respect to this parameter W and V here. So I'm going to minimize respect W, but I maximize respect to alpha here. And you can see the solutions of this problem here is going to be the same as solutions of this problem here. So why is that? Well, because so this alpha here is saying this, well, if your theta here violated those constraints, if your parameter violated those constraints here, and I can well choose alpha to be very, very large number, as a result, this overall function will be very positive infinity. However, if you think about it, you want to minimize this function here, you better make sure that your constraint is satisfied. Because only is satisfied here, this contribution, the overall component is 0. So as a result, these two here, in fact, they are equivalent. It's just a trick of kind of removing this constraint, and such that I can only focus on rewrite the problem this way. So the problem rewrite this way doesn't help you at all, because you still need to solve this maximization problem internally, given a particular choice of theta here. So it just, one way to think about this problem does not necessarily mean that it helps you in any way. However, the way that once we rewrite this problem this way, so now we can rethink about this problem here. Essentially now, I have these functions here. So this function is both a functions of theta and the functions of the alpha. So I can now collectively think about this as new functions here, both the function theta and the alpha here. And so this essentially the solution here is this. I want to minimize the theta, while at the same time want to maximize the alpha. So maximize the alpha here. And so essentially we're trying to find something called a saddle point of this problem here. The reason it's a saddle point here because you have two sets of parameters. So one set of parameter you want to minimize it, and the other set of parameter you want to maximize it. So it looks like a saddle, right? Look at a saddle here. So in some direction you want to maximize, but another some direction you want to minimize. So in general, and so essentially you can think about the solutions of this problem here is try to find a saddle point of this problem here. And in general, that's we can think about how to solve this problem. So, and then there's one more thing I should mention here. This alpha sub I here is something have a specific name in the community. People call it the Lagrangian multiplier. So, so we have one multiplier for one constraint, and because we have m constraints, so overall we have m Lagrangian multiplier. So the alpha here, in fact, is going to be dimensions of m. Because we have m samples. We have one multiplier for one sample. Overall, you have m of them here. That's one thing. So another thing is this. So we actually know for sure. So the solution to this problem, right, as I just mentioned that, if your theta here is say if your g theta here is strictly negative here, if strictly negative, and then we say that if in that case, the optimal solution alpha is 0. That's what we said, right? Because in order to maximize this function here, if your function here is negative, and then the best way to maximize this function is just set alpha sub I to be 0. So that's one thing we know for sure, right? So if your constraints is strictly negative, and then your Lagrangian multiplier is going to be 0. So that's one thing we can say for sure. And this is something called complementary slackness. So if your G sub I is negative, then alpha sub I is 0 here. So on the other hand, so if your alpha sub I is positive, which means that this guy here is going to be ought to be equal to 0. So overall, you can write down these two constraints to be something like this: alpha I G sub I theta is to be equal to 0. So one of them has to 0. So either this Lagrangian multiplier is 0, or your data is at the boundary of the constraints here, which means G sub I theta is 0. And this is something called complementary slackness. So that's what we can conclude so far. So far, I have not provided a solution yet. I just reformulate the problem into this way, and then I'm hopeful that I can find a solution to this problem in an easy way here, right? So this is essentially the one way to think about this problem. So let's think about how do we go beyond that? How do we actually solve this problem here? The question: how do we actually solve this problem? So now I have this Lagrangian multiplier here. So that I'm going to go through the next one more steps here. So that's one thing kind of interesting here. So let's look back here. So essentially now what I did so far is this. I said I'm going to minimize W and B here, and then at the same time maximize this Lagrangian multiplier for alpha here. And then with this functions here, W here, and then I have this summations of alpha I go from 1 to n, alpha I and G sub I, and theta here. Theta itself, I can rewrite that there. So rewrite that. Is 1 minus y I here times W dot x sub I plus B. So that's the problem we're trying to solve here. I'm going to maximize respect to the right-hand side here, but then I'm going to minimize respect to W and B. Right, so that's the problem we're trying to solve. This is the same problem as in our original constraint optimization problem. You can use this Lagrangian multiplier to remove these constraints. So what I'm going to do next is this. I'm going to do one step that is not so obvious, but I'm going to do that. So what I'm going to do is this. So I'm going to change this to this. So right now I have this minimization with respect to W and B, and then maximization with respect to alpha. So what I can do is this. I can switch the orders. I can do maximization with respect to alpha, and then minimization with respect to W and B. Switch orders. I can do minimization with respect to W and B first, and then later on do maximization with respect to alpha. And then by doing that, I have this something like this. All right, so I have new problems here. So now this problem is interesting because now if you look at this side here, so I'm going to change this problems here is a minimization with respect to W and B. And if you look at the right-hand side here, what W and B is simply more or less a quadratic functions of W and linear functions of B on the right-hand side here. And then there's no constraints anymore. So constraints are eliminated. And now if you ask people, say, what are the solutions to these problems here, highlighted by the red lines here? And then in fact, that solution, you can easily solve it analytically because it's a quadratic minimization problem. And then I can find a solution by calculate gradient derivative of this function, quadratic function with respect W, respect B, and set to 0, and can find the solutions to that. In fact, if you do that, if you calculate gradient of this function with respect to w, what do you have is this? And then the 2w here. 2w is a gradient of the square, norm square here, times w here. And then the, so by the way, let me do this one here. So many times people do using 1/2 to eliminate, so it doesn't really matter, you just scale and factor in front of that. But by doing that, when I calculate gradient here, I simply do a w here, and then plus, so I first calculate gradient with respect to w here. And then the right-hand side here will be summations of I, alpha I, and then to be yi, xi here. So that is the gradient with respect to w here. And then there's a negative here. So it should not be plus, should be minus here. And that equal to 0. So that's interesting. So this is saying that solutions of your w here is going to be simply equal to w equal to this guys here. This guys here. Simply saying that the optimal solution to w here is simply equal to summations of alpha goes from 1 to m here to be yi xi here. And if you, so under the condition that if you know your Lagrangian multiplier, if you already find a solution, and then that solutions of this weight parameter is very easy. So that you can see clearly that from this guys here. And in fact, you can plug in this optimal solution into this equation here and then derive quadratic functions of that. And then, so this overall is going to be quadratic, becomes quadratic functions of the alpha. And you can see that. And now what you can do here, you convert these problems here to be simply maximizations of alpha here. And now you plug in the functions w star here into this guy here, and then remove the w and the b here. And then what happens is that you only have remaining alpha remaining on the right-hand side of that. But then I should mention here, this should be to be positive here, non-negative. And then now become a function on this functions of this alpha here only. And that's something you have derived a new set of problems. And what are we going to talk about here, okay? All right, so this is what I talked about so far. So what I talked about so far is this. So the optimal solution to this problem here, w here, is going to be summations of alpha I, yi, xi here. And remember this. What we said previously, alpha I is going to be equal to 0, or g sub I is going to be equal to 0. So g sub I is this hyperplane here. If I add the boundary and g sub I are zeros here. Essentially, you're saying is, if for the data inside, so away from the separating boundaries here, the g sub I will be 0. So alpha sub I will be 0. They are positive only on those exactly on the margins of that. So that's what we derived from previously. So which means, even though here you have the summations of alpha, summation over I goes from 1 to m here, only a small number of terms are not 0, because many of this alpha sub I here are 0. Only on those data points that are located exactly on the margins, they are strictly positive, so they are not 0. And those guys here are called support vectors. Support vectors here. The reason called support vectors is because, so even though your W is summations of a combination of all the data set training samples here, but in the end, only those data samples located at the boundary matters, because only those ones here have a non-zero alpha sub I, and hence you have the supporting vectors here. Those data points here, your W here are mainly depends on those supporting vectors, supporting data samples of that. And the B can be calculated by simply say that the supporting samples here, and those Y is going to be exactly equal to W times X here, right? Because it has to be satisfied the margins of that plus 1, so that's be equal to B here. So that can be relatively down here. Essentially, And because this data set and a margin, so you have to satisfy the conditions. So for instance, this data set here, yi here, and so which means w dot xi plus b is going to be equal to yi exactly for those data points here with this correct w of that. So as a result, so the w can be calculated by verifying the difference between them. So that's what's calculated here. All right. However, I talk about so far this. Suppose if I know the alpha, so that's what I say. If I know this Lagrangian multiplier, and then I can find w and b here, and I found that the solution to w in a very simple form is simply the combinations of the training samples. In fact, training samples x here, and with the weight determined by alpha sub I. However, it turns out that alpha sub I only are non-zero, only for those data located along this separating hyperplanes, exactly on the separated plane. So which means this is actually solution is interesting. Interesting in this, the solution here, the data here does not contribute to your solutions. Suppose, which means, suppose now somebody tells you a new set of new data is here. So that data actually doesn't impact your solutions, no matter how many data points you introduce to the problems here. So that's interesting. So only data that is located on the boundary, because those are hard examples, hard samples. Only those hard samples, ambiguous samples, contribute to the W and B. So that's what it means here. Okay. All right. So now, as I mentioned that if you plug the W hat into this function here, and then you remove W, remove B, and what happens next here is it turns out to be have functions, only functions of alpha here. And that's only involves a little bit of algebra because it's simply a quadratic function. And you can expect that this is going to be quadratic functions of alpha as well. So in the end, you will see solutions look like this, just through a little bit of algebra here. So remove that optimal values of W here and plug into this right to this side here, to this here, remove W and B, and then what do you get in this guys here? All right, so now it becomes only a maximization of with respect to this Lagrangian multiplier alpha here. And then you have this new function here. And then there's another constraint, you want to make sure this is 0 here, since derivative with respect to b equal to 0, because I didn't mention this guys here. So if you do, right now I did derivative with respect to w, and I got this equation here. And now if you say derivative of this guy is here with respect to b here, and what happens here? Well, this guy is here equal to, with respect to b, that would be simply wi alpha I, yi here. This is derivative with respect to b. So that has to be equal to 0. So that's additional constraint that I need to satisfy here. So that was written in this side here. All right. So now, essentially what you have here is this. So you convert a problem into a new problem here. So this problem is trying to say another kind of constraint optimization problem, try to maximize these functions here. The function here is a quadratic function, so that's just like what we did before here. But in respect to this set of parameter alpha here, Lagrangian multiplier here. Okay. So if you know how to solve these problems here, and then you can solve the original problem then. So this problem has a name, something called it's called dual problem in this community. It's dual problem here. And so the problem originally formulated in this way is called a primal problem. So this is called a primal. And later on, this is called a dual problem. So the reason these two problems here is interesting here, because if you go back to the notes I just wrote down over previous here, essentially, this is a primal problem here. This is a primal problem. And this is a dual problem here. So the difference is this, we switch the orders of our operations here, right? So we have this minimization min max here. In the primal, we do maximization first and then later on do minimization. So in the dual, we do minimization first, later on do maximization here. So that's the difference between the two here. So in general, the dual solutions here is a lower bound of the primal solution. So what I mean here is suppose this is your optimal solution here, minimize over this guy's here equal to D here. And you minimize the solution here equal to P here. Equal to P, and this is equal to D here. So there's optimal values of the function after you're solving the optimal. In general, D is less or equal than P in general. So which means that there is something called duality gap between these two problems here. So these two problems in general, they're not equivalent. And which means that the solution of this problem may not be the same as the solution of the primary problem. However, for the problem we are considering here, and because the function forms we have, because it's a quadratic function, and the constraints are function in general because it's a convex function here. So in this particular case, these two problems are actually equivalent. So we can say that these two problems say, if you find optimal values of this problem here, and then the problem is going to be exact solution of the primary problem, which means that there's no duality gap for this problem. Duality gap. So this is just a technical term. I just want to say that because some of you wonder, if I switch the order here, how do I guarantee these two problems are the same? So in this case, they are indeed the same. So you can prove it, but I will not go through the detail. I just want to say that. So that's the benefit things here. That's what if you know how to solve the dual form, so that can solve the original form and vice versa. So these two ways of formulating the problem are the same here. So what the question is this, right? So still, this does not mean I have ways to solving the problem. I still don't know how to solve the problem because the dual form is still a constraint optimization problem. And of course, we have ways to solving that by using something called a convex optimization and take care of the constraints we have. And so people have sorts of methodology for solving that. But however, let's say if we think about how do we solve the problem ourselves, right now it's not so clear. The method that we are familiar with right now is this unconstrained optimization problem. So the question is there any way I can convert this problem into a completely unconstrained optimization problem? And so in that case, I will be able to solve it. So right now, it's a little bit hard because so I cannot solve this problem exactly because even in this way here, when I introduce this Lagrangian function here, so when I minimize the respect W, I have to plug in some alpha here. So I can try for different choice of alpha, but in general, remember that I have m Lagrangian multipliers. I have many of them. So it's very hard to try all combinations. So that's not a feasible way to do it. So we need to sort out some other way of solving the problem. All right. So that's one thing. However, I'm going to come back here and revisit this dual form here. But now let's think about other problem here. So another problem is this. So in this formulation here, I need the constraints to be completely satisfied. So which means that your original data sets need to be linearly separable. So what happens if data are not linearly separable? So what happens then? What if data are not linearly separable? You just cannot put two lines such that they're separate from each other. It's just impossible doing that. So we have to relax our current formulation to allow this type of certain errors to introduce before the problems there. So the way we're doing this is this. We're going to relax the constraints. So previously, we say that we want to make sure these two data sets completely separate these two groups of data points here. But right now, what happens if data sets are not linear separable? So we cannot achieve that goal. The way of doing this is saying we're going to relax some constraints. So remember that, so originally this is a function here we want to satisfy. We want to say this score here is strictly greater or equal than 1. So that which means they are above outside the two separating hyperplanes. So now I'm going to relax that constraint, say it does not need to be greater than 1. I can relax the constraint by introducing something called epsilon here, say, and allow it to violate this constraints a little bit here. So for instance, I might have two separating hyperplane this way, so this way here, and then there's another separating in the red lines here. So now within the two lines of them, there are dots, they are violated as constraints here. So they are, so they are not separated. They are actually mistakes. So we're going to do that by introducing these epsilon variables here. So these are values. How much you are violating those constraints here, violating these margin constraints here. In general, we require them to be non-negative because to extend over the violating constraints here, which means they have to be positive numbers for that. So the way we're going to do this, well, so we're gonna introduce additional so-called slack variables here. Those slack variables here, essentially these violations of the margin constraint. So the way we're doing this, we're still going to minimize this your inverse of the margin here, maximize the margin here, and but the constraints now is a relaxed constraints here because some data sets are going to violate this separating constraints here. But however, we're trying to encourage you to have as small violations as possible. So that was used in this term here. We try to, when I minimize this the square of W here, at the same time, I try to minimize the overall slackness of the margin violations here, the summations of these epsilon variables. So because these epsilon variables are non-negative, so if I try to reduce the values and I'm encouraging the solution, find a solution such that the less violation on the solutions. Of course, there need to be balance of the two here, whether you are encouraging the margins or encouraging the violations of the constraint. So that is controlled by this parameter R here. So R is a parameter saying how much you're going to weight on these violations of the margin or the magnitude of the margins here. So if R is very large, so which means that you put more weight on this separating constraints. You want to reduce the slackness of their slack variables. And on the other hand, if R is very small, so in that case, it's saying that slack variable does not contribute much to the loss function. I try to find the separating the solution as separate as possible. So that's two balances these two. Okay, so that's one way we're going to solve this problem here is by introducing the so-called soft margin by introducing the slack variables. So let's revisit what we talked about so far. So now what we talk about here is the constraints is relaxed here to introduce this additional slackness into the constraints here. But at the same time, we try to minimize this overall levels of slackness, try to make sure encourage it to be as small as possible. So there's a few examples here. So this is R with the reasonable levels of this slackless constraints here. So you think about these two solutions of that, and I have these margins here, and right now these two solutions here are more or less separate here, right? So they're linear separable. So now suppose I'm going to reduce those slackness constraints I have here. For this problem here, so these are relatively smaller slackness constraints. So in this case here, essentially we encourage you to increase the margin. So that's what they're doing here. You increase the margin, your margin is bigger. But then there are a few data sets here are violating the constraint you have here. You can see these two data sets are within this boundaries. So you have this slackness here. From this side, here. Summation, this is the epsilon here, and this is the margin here. You can see now because you are encouraging margin, you get a solution like this. Now, if you further encourage the margin here, now you have margin is even bigger here, and now you have more slackness introduced here for this guys here, and this is this guy here, Yeah, you have more. So it's kind of weighting between these two parts of that. So usually this is a hyperparameter, and then we have to choose using cross-validation procedures. Okay, so that's what are we doing so far. Well, so this is interesting. So I should comment on that. So the soft margin here is certainly necessary for linearly non-separable cases. And however, even for linearly separable cases, sometimes it is people may encourage you to introduce the soft margin because. And for instance, for this example here, even though these two data sets are linearly separable, however, I feel like the margin between them is not too large. Suppose I want to encourage the generalization between the margins. Let's increase the margins. So I'm willing to sacrifice make some mistakes here, but as a result, that my kind of margin is bigger. So as a result, so they can see that it's balanced. So even for linearly separable cases here, I might want to use this soft margins. So it's a more general case here. All right. So let's review what we talked about so far. So we have introduced so-called soft margins here, and the new problem is formulated as this guy's here. So again, is a constraint optimization problem. So I have this objective function here, satisfy those set of constraints. However, so in this case here, so this problem here is interesting because interesting in the sense this. I can actually now think about what are the solutions to these problems here. So let's think about it here. Let's think about this slack variables here. The slack variable is saying this. So the constraint is saying that the epsilon here need to be greater or equal than 1 minus y I w dot x sub I plus b. So that is this constraint saying this. So the slack variables here need to be greater or equal than these numbers here. Okay, so that's what this constraint is saying. So now let's look at it here. So in my original objective function here, I need to minimize these guys here, minimize the slack variables here. So you have two sides here. You want to find a solution, minimize this, but on the other hand, you know that this guys here it has to be greater or equal than this variables here. So what happens? Well, the best solution you get is going to be 1 minus y, exactly this solution here. Because if you minimize that, this is the lower bound you can reduce, and that well solution might be just this guys here. So, however, I should mention that there's one more constraint. The other constraint we're saying that this guy slack variables here is to be non-negative, so it's to be greater than 0. So which means that when I minimize with respect to epsilon here, and it's going to be either this solution or this solutions here. Whatever is bigger. So which means if this is a positive, it's going to be this. If this is negative, it's going to be 0 here. And so which means, so this constraint optimization problem, I can rewrite them. The epsilon here is going to be the optimal solutions here is simply going to be the larger value among the two here. Max either 0 here or 1 minus y I w dot x I plus b. So that's what this says here. Right, so which means I can just substitute this into this in the objective function here and then remove the constraints because I can find a solution to that. If you do that, essentially now you can rewrite your objective functions here into linear problem into something like this guys here. So let me highlight that into something like this. So let's look at this guys here. So there are two parts of that. So original part is this part here. So let me remove R to this guy here. Let's rewrite R to be this guy here. Okay. So you have this original inverse of the margin constraint, and then this guys here is this solutions here. In this solutions here. And what you can see is this. So if you define this to be this guys here, right? If you define J sub I to be this, simply the solutions of that. And R is this, the parameter that I have here. So now, if I do this, first of all, I should comment on that. So now, essentially, now it becomes a minimization of a problem here. There's no constraints here, right? So however, I should mention that essentially I absorb this constraint into this function here, maximization with maximization over two variables here. But now let's rewrite this in here, rewrite them. So I'm gonna change R, switch, divided by R to side here, remove R to this side here. So now I have two parts in this function here. So one part is this, let me think about it. One part is this guy's here. And then the other part is this guy's here. And now it looks very familiar to you now, right? So what is this? Well, you can think about it. This is my loss functions here. And then this is a regularization term. And in fact, is L2 norm-based regularization term here. And 1 over R is this regularization parameter previously we talked about here. And this guys here, you can think about it, is a one kind of a loss function here. And well, essentially, the way we formulate here, it looks like it's very close to our previous formulation. We say, without talking about a margin here, we're just trying to solve a optimization problem by formula a loss function. It looks like this SVM, soft margin versions of SVM, is equivalent to minimize this loss function subject to this L2 norm regularization, but with this type of loss function here. So now let's look, what does the loss function look like? So now, essentially here is this. So if I use the previous notation here, this is our score here, S here, right? And this is the sign here, if this is positive or negative that. And this function here essentially is a piecewise linear function of the score itself. Suppose this is score here. Right. Suppose now your actual label y here is positive 1 here, and this is what this function will look like. This loss function will look like. It will look something like this black lines here. So what is saying this? It's saying that if your score is greater than 1, I'm talking this loss function terms here. If your score is greater than 1, and then the loss is 0. So why is that? Because if your score is greater than 1 here, the 1 minus that score is negative. So maximization between 0 and negative. So it's going to be 0 here. So your loss will be 0. And so essentially, so 1 minus loss here. So now, if your loss is very negative here, essentially now becomes 1 minus negative score become positive score here. Is a 1 minus of S. So that you can see now goes to like linearly on the very negative side of that. And you have loss function looks something like this guy here. All right, so let's rewrite it here. So that's my new loss function. So let's talk, what do we talk about so far? So we're saying this, our model here is a linear model. I have a score here to be W dot X plus B here, I have score here. And now I have a new way to formulate the loss function. So loss function is this. So give me a pairs of data X and Y here. I suppose now Y is 1. Suppose Y equal to 1, consider the case. And the loss function looks something like this. So there's a maximization between 0 and 1 minus score, if Y is equal to 1. So this is a score here. And it's saying that if your score is greater than 1, there's no loss. So your loss is strictly 0 on this side of that. And only become a non-zero loss when your score is less than 1. So that is your new loss function. So this is a loss function here. Is equal to this guy here, when Y equal to 1 here. So that's interesting. It's saying that the soft margin versions SVM is nothing, just using this type of loss function. This type of loss have named something called a hinge loss. The reason called a hinge loss, it looks like a hinge, right? Kind of it's saying that if it's greater than 1 is 0 and only non-zero is 1. So what's saying this, right? If your score is significantly higher than 1, you are doing correct prediction. I impose no loss. So I'm going to impose loss only when you're actually less than 1. So previously we're saying that, well, if you are negative and then you are essentially making the wrong predictions. However, between 0 and 1, so you are not necessarily making the wrong prediction. Your prediction is still correct. But however, you are not make prediction with a large enough score. So that's the reason we still impose certain loss, not great, but certain loss of that, not big, certain loss of that. So that is, so you think about that, how is this loss compared to the cross entropy loss? I don't know if you think about that. So this is a hinge loss. If I were to plot previously the negative log likelihood loss, it looks actually pretty similar. It will look something like this if you want to compare them. This is a cross entropy loss, what cross entropy loss look like. So first of all, I should comment on that cross entropy loss is completely continuous, right? So it's not going to be strictly zero, no matter how big is your score. So even your score is very large, we're approaching zero, but not exactly zero. So that's one thing different between this cross entropy and then this is cross entropy. So this is a hinge loss. So however, the overall trend is very similar. Essentially now, if your score is very negative, so in that case, your log likelihood is is very negative. So it's very large. So negative log is very large. So in that case, you impose a very big loss on the constraint on the function of that. So the only difference here is for the hinge loss, it is piecewise linear, and also it's kind of have a hinge point here. That is have a switching point. Unlike the cross entropy solution, that is kind of smoothly going up of them. So otherwise, they look very similar in terms. If you look at their loss function, they look very similar. So in summary, what do we mean here is this. So let's go back to what we talked about so far. So what do we talk about so far saying this? Well, the problem I talk about here is essentially the soft margin SVN can be understood as minimize a loss function subject with this L2 norm regularization. The only difference now is that this loss function is something like a hinge loss function here. It's not a cross entropy loss function. All right. So once you have these guys here, so now we know how to solve this problem because I can simply apply gradient descent on this objective functions here. So I can do that. So however, there's one nuance I need to kind of think about because this hinge loss function here and the gradient, there are two parts. So this part here is the -1, this part is 0. However, at this point here, the gradient is not defined because it's not differentiable. So however, I don't need to worry too much about it because there are very few data points that will be exactly at this point here. So most of them will be either to be less than 1 or be greater than 1. So the gradient could be either -1 or 0. And so numerically, you will never reach the exact number. So we don't need to worry too much about that. So even if we are exactly here, you can choose either 0 or -1 here. And then by doing that, I can have a methodology of solving this SVM problem here by simply using gradient descent methodology. And simply calculate gradient with respect to this hinge loss function. So even though it looks a little bit strange, but you can still calculate this gradient. So strictly speaking, the gradient does not exist because it's not differentiable, and that's the reason people call it something called a subgradient. So subgradient essentially say that what is gradient at this point here, what does not exist. And now you talk about what subgradient at this point here is something between -1 and 0, and you can choose any number between them. And if you do this, and you can derive a gradient descent-based methodology for solving this problem. Okay, so that's what we talked about so far here. And then so let's look at the dual forms. So dual form is so by doing that, essentially, I'm going to tell you a way of saying this. Well, I somewhat have a methodology for solving it. So that's all good. And then let's talk about here. So what are the dual forms of this problem here? Suppose I do not eliminate these constraints here. I view them as constraint and still introduce the Lagrangian multiplier. What does the dual form look like? So in fact, the dual form looks very similar to the previous one. The only difference here is you constrain Lagrangian multiplier not only to be non-negative, but also is upper bounded by this regularization parameter alpha, R. And then this is a dual forms of this soft margin problems here. You can see that's very similar to what we talked about previous. The only difference here is this. So the Lagrangian multiplier here is not only to be non-negative, but also upper bounded by R for each one of them here. And the solution is the same. If you look at the solutions here, your predicted W here is going to be summation of a set of Lagrangian multipliers here. So summations of the support vectors here. and the supported vector will be, so however, so now it's slightly more complicated because your R here is because it has upper bound in here. So your supported vectors here is going to be not only those located in the boundaries here, but also including the data point that are violated by those constraints. So for instance, your supported vector here not only include those points located in the boundaries, but also located this red dots here. The deep in the blue region, because those variables here essentially correspond to the slack variable introduced to for this violating this separating. So your in that case, so your alpha sub I is going to be have a slightly more complicated than previous case. So we need to include supported vector will be including those data point predicted incorrectly. So, so otherwise, it stays the same here. So supported vector will include dying on and past the margins here, including those exactly on the margin, but also already overpassed the margins. So those are supported vectors in the version, the soft margin version of the models. Okay, so so that's what the supported, but in general, still the case. For training data sets here, for those data well within the boundary of them, they have no impact on the learned parameters. So that's one thing is very special. So this is not the case for the cross entropy, for the logistical regression models. So in the logistical regression, every data point contribute to the learning parameters of that. However, for the SVM models of that, and those data points, if they are well within the boundary, within the interior of the decision boundaries, they don't contribute to your parameters, the W and B here. And because only supported vectors contribute to W and B. So that's interesting characteristics. All right. So so I have a few minutes here. Let me pause here to see if you guys have any questions, because this part here is involves a little bit of math here, especially involves the constraint optimization here. So for the next lecture, I'm still going to continue to talk about this and try a few other topics I'd like to go over them. But let me actually pause here to see if you guys have any questions. All right, so looks all good here. Well, if that's good, let me mention one thing here. So every framework I talked about so far, let me summarize what I talked about so far. Here it is. So I have this maximizing the margin framework of that. And I talk about that, saying that, well, in the soft margin optimization framework, I can convert that problem into something called a hinge minimize the hinge loss function with L2 norm regularization. So that's the equivalent. So under this framework here, I know how to solve it. So if it's for the constraint optimization problem, there are methods for solving that. So that's, in fact, most SVM solvers are based on solving the constraint optimization problem. Very efficient way for doing that. The problem we talk about here is very specific. So is minimizing a quadratic function subject to linear constraints. So for that type of function, we do have a solution, efficient solution for solving that. And however, you don't need to know that. You just need to implement a gradient descending methodology for solving this type of problem here. And then, one thing about so far, by introducing the dual form, we know how to characterize solutions to the problem. The solution to the problem is saying this: your weight parameters here only depends on those support vectors. So that's a very important step, because only a few support vectors are located along the boundaries or passing the margins of that. But only a few of them. Majority of them are within interiors of the decision boundary. And those data samples, in fact, have no impact on the solutions. So this is actually very interesting here, giving you a lot of thoughts on the solution to this problem. So this is saying that, always people ask you, is this the case that the more training data, the better? So people ask this question. Well, based on this is not necessarily the case. And if you have lots of data sets located with this point here, it doesn't help you. Your solution stays the same. Similarly, if you have lots of data inside the interior of this point here, even slightly off the boundary, that doesn't help your solutions within the SVM framework. So what you need are those hard samples, hard examples. They're located along the boundaries of this example. That's what you need. And only those examples here can change your solution. Otherwise, it would not. So that's kind of interesting perspective. That the reason for that, by introducing this dual form, we derive that why this is the case. Okay. So there's another thing I should mention here. What's the difference between primal and dual? Well, if you think about here, the number of variables involved in the primal and dual are different. What I mean here, well, in the primal, we are minimizing with respect to W. How many parameters we have? What depends on dimensions of your input. So that'll be N here. How many variables we need to optimize in the dual form? What that's actually the dimensions of the number of samples we have is the M here. So that's kind of interesting. So it depends on whether your M is greater or less than N, you might choose one solution versus the other. So for instance, if you have many samples, if you have lots of samples here, M is much greater than N. So that doesn't come very often, but sometimes you do have that case. You have a lot of samples, but then a small number of features. So in that case, the primal is a better way for solving this problem. On the other hand, if you have lots of features, but only have a smaller number of samples, M is less than N. So in fact, the dual form is actually could be a better form of solving the problem because it involves less number of variables. So that's interesting. Well, that's the reason. So the SVM was originally proposed to solve exactly this type of scenario, so that you have a small number of samples, maybe 10, 20, 100 samples, but you have many features, or hundreds of features. And how do you handle that problem? And then by maximizing the margin, and then that can kind of enforce the constraints strong constraint on the model of that and help you provide you better solutions. So that's the dual form stuff. So one thing I want to quickly mention here is this. And well, right now I talk about binary classification. So how do we generalize this to talk about multi-class classification? So for the probabilistic models, and we know how to generalize that. We go from binary cross entropy to a cross entropy by introducing the softmax functions. So that can easily do that. What happens for the SVM? Well, you can do that as well. Essentially, the framework, what we do here is to generalize this hinge loss function. So I'm going to do this very quickly over this quick video. Essentially saying this, well, I'm going to minimize again this the regularization parameter here, but then with margin here by introducing slack variables. But this slack variables now is going to be doing all the pairwise comparison now. So which means if you have given me a ground truth data sets here, so this ground truth targets that. So I want to say, what is the score associated with other samples? I want to make sure the score associated with other samples here is less than this sample corresponding to the ground truth target and within the margins of that. And so that's how do we do that? Essentially, one minus this guy here by going over all different target labels of that. So that would be very direct generalization, extensions of this binary margin to the multi-class margins of that. So that you can do that. So that's also doable for doing that. So the next thing I want to talk about next time here is I'm going to talk about how do we actually generalize this kind of a model from linear classification to a nonlinear cases. And this is actually one of the kind of very important implications of the SVM models is this, right? So I can derive kind of nonlinear decision boundaries relatively easily throughout this framework here. So I'm going to talk about the next lecture by using this idea, something called a kernel trick. So by introducing kernels of that. By doing that, we now can have nonlinear decision boundaries. So that will be